Okay, so welcome to the ninth video in the Discrete Structures series, and we'll start this video with a quick discussion on sequences. We'll define this formally and then we'll look at various ways of describing sequences, and that will include describing sequences as an indexed-based function and also as a recurrence relation. And then we'll move on to the types of sequences. And here we'll be looking at three basic types of sequences that we've already known: the arithmetic sequence, the geometric sequence, and the harmonic sequence. And for each of these sequence types, we'll describe their properties and identify their general term. And then we'll move on to a topic that I want to call identifying sequences. And this is mentioned as special integer sequences in your syllabus, but this name might be misleading. It doesn't actually refer to any special sequences, but it refers to the process of looking at practical data and identifying patterns in it, identifying the sequence that a given set of data represents. And then in a related context, we'll be looking at the strong law of small numbers. And let me give you a hint of what this suggests. It basically states that there are too few small numbers to meet all the demands that we make of them. Okay, and we'll see what that means when we get to this topic. So let's get started with an overview on sequences. Let me get some space. So sequences. To the core, a sequence is just an ordered set of numbers. And it doesn't have to be numbers. It can be, let's say, an ordered set of functions or any mathematical object for that matter. So I could have a basic sequence of numbers like so. And for another example, I could have a sequence of the uppercase letters. And to take home the fact any object, I could have a sequence of all the videos that I posted on this channel. But whatever the type of sequence it is, the concept of cardinality always holds. So what do I mean by that? So even if this is a sequence of videos, I could tell that this is the first element, this is the second element, this is the third element, and so on. So in a way, no matter what kind of sequence I'm describing, the natural numbers 1, 2, 3, etc. have something to do with the position of those elements. And that's where the formal definition of a sequence comes from. Because again, you could think of this as a mapping. This is a mapping between the set of natural numbers containing 1, 2, 3 with anything on the other set, right? It could be, I could borrow it from here, I could borrow it from here, or any other sequence. But the idea here is there is a mapping. Therefore, the formal definition of a sequence states that a sequence is a mapping from the set of positive integers, which is also the set of natural numbers, to any other set or collection. Now let's have a look at ways of describing sequences. And there are two common ways. Let me draw two columns. One way is to describe a sequence as a function of the one-based index. And second way is as a recurrence relation. So looking into the first one, what does one-based index mean? Remember, we define sequences as a mapping from the set of natural numbers, and that starts with 1. Whenever I write a sequence like, let's say, A, B, C, etc., I say that A is my first element and B is my second element, and it goes like that. So I start my indexing at 1. Many programming languages use a zero-based index, right? So an array representation in a programming language like JavaScript would say that the first element is in 0th index. And doing this has some advantages that we're not going to get into the depths of, but we'll just follow this as a convention, okay? This is just a convention. Getting into the core of this, consider this sequence. So this sequence starts with 1, and each new term is obtained by multiplying the previous term with a 2. We'll look into the general term of a sequence like this shortly, but I want you to consider this. If I write a of n equals 2 to the power of n minus 1, and my claim is this equation is a representation for this sequence. And in order to generate terms for this sequence, all I need to do is to start plugging values into this equation, starting with n is equals to 1, right? When I plug n equals to 1, I get a 1 because 2 to the power of 0 would be a 1. And then if I plug n equals 2, I get the second term. If I plug n equals 3, I get 2 squared, and that's 4, and which is the third term, right? In general, if I want the nth term, I can simply plug n. But the focus here is not this particular equation. The focus here is that this equation is written in terms of n, the one-based index defining the position of items in this sequence. And to demonstrate the other way, let me make this assertion, because I can tell that each number is increasing 2 times from the previous term, right? So I could say that any term a of n would be 2 times the previous term. And this fact is true for the given sequence. But is this enough information for me to regenerate this sequence? Turns out it's not. This equation only provides me value for the current term based on the value of the previous term. It doesn't give me where to stop. Therefore, each recurring definition must have a base case, also called a termination case. And in this case, as I'm tracking items back from my sequence, I end up at 1, and then the rule doesn't apply anymore, right? I cannot tell the 1th term is 2 times the 0th term because the 0th term doesn't exist. Therefore, the base or the termination case for the sequence would be a1 equals 1. And using these two facts, I could regenerate the sequence. I'll start with my first term, 1, and then I know that the second term would just be 2 times the first term, whatever that is. And in this case, the first term is a 1, therefore the second term would be a 2, and so on. So this is also a perfectly valid way of defining the same sequence. But there is a very important thing to consider here. This way of defining sequences must be preferred over this one because this has a very typical advantage. In order to get any term, I can simply plug in the index and it will calculate me the value of the item in the sequence. So for example, if I wanted the 50th term, I just need to plug a 50 here, and I know that's 2 to the power 49 and whatever this number is. All I need to do is to make one arithmetic calculation. But if I need to solve the same problem here, this equation doesn't tell me much. It only tells me that my 50th term is 2 times the 49th term. And then I have to proceed recursively. I have to ask then, what is the 49th term? And that will throw me deeper and deeper into a pit hole until I eventually reach 1, and when the base case allows the recursion to resolve. So this is to be preferred, but there are certain problems that can only be solved with a recursive approach, okay? And that's where these find their applications. Okay, so the next topic that we'll be looking at are the types of sequences. So the types of sequences, and these are quite simple facts that we already know. So I'll just go through them quickly. The first one is arithmetic sequence. And these are sequences generated by taking a starting seeding number, let's say 2, and then adding a constant difference to it. Let's say I want to add a difference of 3, then I end up with 5, add the same difference, I get an 8, and then it goes on. So in terms of definition, an arithmetic sequence is a sequence in which the difference between two consecutive terms is always same. And to generalize this concept, let's say I didn't start with 2, but with any number a, and then I added a difference, not 3, but a general difference of d. That would give me the second term a plus d. And let me index these. This is my first term. This is my second term. And then in order to reach the third term, I want to add one more d. And therefore, I would be at a plus 2d. And remember, this is for index 3. And by the way, this is also 0 times d, right? And the pattern here is, to get the first term, I need to add 0 differences. To the second term, I need to add 1 difference. Here's 1, and so on. So in order to get to the nth term, I want to take the first term and then add n minus 1 differences. So there's another sequence called a geometric sequence. And the idea here is, instead of having a common difference, we want to have a common multiplier, a common ratio. So these would be sequences that look like, let's say I start with 2, and instead of adding 3, I start multiplying with 3. So 2 times 3 would give me 8, and then 24, and so on, right? So this would be a typical geometric sequence. And the ratio could be a fraction. For example, I could take 2 and start dividing by 2, for example, and then I would get a 1, and then I would go to 1 by 2, 1 by 4, 1 by 8, and so on. And to generalize this, let me start with a, and this time instead of adding, I want to multiply. So the second term is a times r, and the third term is a times r squared. And there's a similar pattern to this. If I look at the first term, this is really a times r to the power of 0. and this is r to the power of 1. So here I added 0 differences, I'm multiplying 0 ratios. I added 1 difference, I'm multiplying 1 ratio. So if I proceed in this fashion, I would reach my general term an, and I could call that to be a r to the power n minus 1. So take the initial term and multiply it with the ratio n minus 1 times. So nothing too fancy over here. I want to move into the topic of identifying sequences next. So let me note that down, identifying sequences. And by the way, this is mentioned as special integer sequences in your syllabus, but the name might be misleading. It's actually about the idea of looking at different numbers and trying to find what sequences they represent if they form a certain pattern. So let's take a look at a couple of easy examples. I want to start with this one. Let's say I have a sequence 1, 3, 5, 7, 9, and so on. So can you identify this sequence? So this looks like an arithmetic sequence because each term is differing from its previous term by the same amount, by 2, right? And therefore I could generalize this should be a plus n minus 1 times d for the general term. And that in this case would be 1 plus n minus 1 times whatever the difference is, 2. And with some algebra, I could say this is equal to 2n minus 1. Okay, one more easy one. Let's say 1, 1 by 2, 1 by 4, 1 by 8, and so on. So this is something that we can also easily identify. This is a geometric sequence with a ratio of 1 by 2 and a starting point of 1. So this is just 1 and the ratio 1 by 2 raised to the power n minus 1 and 1 by 2 raised to the power n minus 1. And I can verify this. If I plug n is equals to 1, I get 1 by 2 to the power 0, which is 1 over here. And similarly, I could generate the other terms. What about this one? 1, minus 1, 1, minus 1, and so on. Is this the type of sequences that we know? So turns out this is just also a geometric sequence with a ratio of minus 1 and the starting point of 1. Because you see, you start with a 1 and multiply with minus 1 each time. So once you do that, you get minus 1. Once you multiply it again, the sign flips and it becomes a plus 1, and then it goes like that. So I could generalize this in a similar way. This would be minus 1 to the power n minus 1. So that for all even powers of n, this just generates a 1. And for the odd powers of n, it generates minus 1. Next, we'll look at a pretty fascinating example that shows you how sequences can often be deceiving in the real world. So let me give you this common sequence 1, 2, 4, 8, 16, and I'll be careful not to write the next term here and ask you that question. What is the next term? And you would be correct to say 32, but that would only be in the case if this is representing a geometric sequence with a starting point of 1 and a ratio of 2. I can show you an example of another physical phenomenon which leads to the same 5 numbers, but the 6th number is not even 32. It's actually 31. So it goes like this. Imagine a circle. Let me consider any point on this circle, and each time I consider a new point, I'm going to generate a new term for my sequence. So I'm going to do that by counting the number of regions inside this circle. Now currently there's only one point. This doesn't actually divide it into any regions, but it will be clear when you consider the second point. So for now, just bear with me. With 1 point, this entire circle only has 1 region, right? And therefore I'll write 1 for my first term. Now when I add my second point, and each time I add a point, I want to connect that point to all the previous points. Now in this case, I only have 1 previous point. I'm going to connect it to that point, and I'm going to look at the number of regions. Now I have 2 regions, and that is the next term. If I proceed in that fashion, considering the third point would create 2 more chords, like so. And then the circle would be divided into 4 regions. When I consider a fourth point, you can count to verify that this now has 8 regions. And introduce one more point if I can. And under this configuration, this curve has 16 regions. Now it is not feasible to show you with a drawing by adding one more point, but if we were to add one more point and connect it to the previous 5 points, you would expect 32 regions, but you could do it yourself. You would only be able to count 31 regions at a maximum. So the main idea here is these numbers can often be misleading. If I look at the first 4 terms, I could not tell for certain which sequence this is representing. And that's what the strong law for small numbers suggests. There are only so many small numbers to meet the infinite demands we make of them. And I hope this is sensible to you. If you look at these two examples, the numbers 1, 2, 4 and 8 are responsible being part of this sequence and this sequence. They have too many jobs. Only looking at these small numbers doesn't give me enough information about the nature of the sequences, because these numbers have a lot of other responsibilities, so to say. It's only when I get to the very large numbers do I get meaningful information about these sequences. Okay, so what this suggests is that small numbers are forced to bear too many properties and it's hard to disambiguate them at times. So I hope this gives you some perspective, and that would conclude the content for this video. In the next video, we'll look at summations and series. We'll look at single and double summations and also some special summation formulas, and then follow up with a discussion of series. Until then, you guys take care. I'll see you in the next one. Bye.